Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Infrastructure Thought Leaders series, Large-Scale Retaining Wall Systems. My name is Amanda Rogers and I will be your host for this evening. Firstly, in keeping with our tradition, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders past, present and emerging. Before we get started, I'd like to acknowledge that tonight's seminar is being hosted by our industry partner, Austral Masonry. Austral Masonry is one of Australia's largest manufacturers of concrete masonry blocks, retaining walls, pavers and stone products. Their residential solutions can be seen on high-end architectural projects and landscaping designs, while their commercial solutions include coloured and standard masonry blocks, large-scale segmental block retaining wall products, as well as a range of hard stand solutions such as commercial and permeable segmental block paving. They offer innovative solutions that provide structural integrity, excellent strength, durability, and pride themselves on making beautiful products that last forever. Please enjoy a short video.
Throughout the past 110 years, the face of building materials has continued to evolve. We're here for a lifetime of living. This is Brickworks. More than brick, and more than just building products, we are a foundation for today's lifestyle and a leader for today's style. We manufacture a wide range of building products like no other. Local and international innovation, sourced from around the world to exceed customer expectations. Distinctive and luxurious products, beautiful products that stand the test of time. Building inspiration and innovation with an unmatched standing of style. This is Brickworks.
I'd now like to welcome our first speaker for today, Namir Asmaro. Namir is a technical systems engineer at United Crib Block Company. He has worked in project engineering and management for civil construction for over 15 years, both in Australia and internationally. Namir's other experience includes technical sales, research and development of geosynthetics and retaining walls for over 12 years, design and construction of segmental retaining walls, and he has also worked in product development. Please welcome Namir Asmaro.
Good evening, everyone. My name is Namir Asmaro from UCBC, United Crib Blocks Construction. We'll be covering Keystone retaining wall systems, and in particular, TW3 system, and share our experience in the walls that we built in Oakdale West industrial project. RSWs were first built about 4,000 years ago in Mesopotamia. Structures up to 50 meters high were built in the forms of ziggurats, worship buildings, where huge ramps and walls were constructed around compacted clay fill in the core of these buildings. Once the exterior walls started collapsing, they exposed this mass reinforced fill, which shows the use of reinforcement in multiple layers of clay. The reinforcement that was used back 4,000 years ago was of reed mats. Closer look, you can see this photo that the reed mats were actually embedded into the clay in layers And on the right-hand side, the photo showing part of these reed mats. These are the genuine reinforcement that was used. So as a science, it was started many, many years ago. Modern reinforced soil walls started in the 1960s by the engineer Henry Vidal with the patented reinforced earth system Terry Army. And after that, different types, different facing finishes, different reinforcement were used in many other retaining systems using the same principle of reinforcing earth. The total of wall areas around the world is currently sitting around 50 million square meters, which is equivalent to Sydney Harbour in area. Reinforced soil walls are composite retaining structures. So utilizing the facing, which can be of concrete, steel, other materials, and reinforcement, which also can be geogrids, polyester, polyethylene, polypropylene, or steel, ladders, or mesh, etc. The key factor in this system is how this facing is connected to the reinforcement at the back. The Australian standard that covers reinforced soil walls is the AS 4678 2002, which is titled Earth Retaining Structures. This standard covers different design considerations, including sliding, overturning, rupture, bearing, etc. But it definitely does include the connection strength. So connection of the different elements, this is clause 3.9, of an earth retaining structure shall be designed to take into account the load carrying capacity of the connection system. Where clause 3.9 notes also refers to the overall stability of the reinforced soil structures. Structure is not necessarily reliant on the stability of the facing system. However, the stability of the facing system relies directly on the connection of the facing elements to the soil reinforcement elements, which explains why at the ziggurat the facing was gone while the core compacted reinforced soil is still there until today. Keystone wall designs use different types of geogrid reinforcement available in the market, mostly uniaxial grids, and the design mostly is also in the fill situation where the grid reinforcement length is 70% of the overall height of the wall. And then that gets longer once for higher walls or high loading walls. So special care is required for when wall is under high loading. But it results also in lengthening the grid reinforcement. With the TW3 system, it uses one type of grids, that's the Tensar HDPE grid. And because of the unique design, this grid gets embedded, gets connected to the facing throughout the whole face. So it results a positive connection between the blocks and the grids through the plastic connectors that you see here in blue, in addition to the pins that are also locating where the blocks are. Doing that, we get a grid length normally is less than the conventional grid for high walls and high loading walls, as well as the vertical distance between the two layers of grids is most of the times in 3 blocks, 600 mil. While with the conventional grids, we find that we need to have a grid of layer every 2 blocks. Oakdale West Industrial Project is a project that UCBC have secured February last year, and we've been working on that project since April, and we're still going. There's about 70% of these walls are now built, a total of 14,000 square meters in 14 separate structures. The walls vary in height between 2 meters and 14 meters. Out of all these 14 structures, we identified at the tender stage that wall number 2 is the most challenging retaining structure that we need to have and look at and consider right from the tendering, designing, and the construction stage. This is part of the challenges that we faced when we were looking at designing retaining wall 2. First is the shape and maximum height, then the properties of the foundation and retained soils, the sound wall that's existing behind the wall, 1.8 meter, and then the fence right on top of the wall. There's a geogrid-free zone at the top 1 meter of the wall. That's required by the client. And then there's an existing service right in front of the wall, where the wall is in the zone of influence, which also needed some special attention from us. To show you the wall elevations, this is wall 2. So it's a 336 meter long, goes up to 14 meters in height at this section here, and a total area of 1,800 square meters, just about. The other challenge is the shape of the wall. It's not a consistent height along the wall. It starts from 0 and goes up to the maximum height of 14 meters at chainage 50. And then it tapers down to around chainage 200, 150, where it then becomes consistent in height or close. The other challenge was the soil properties, in particular the foundation soil, where actually in the highest part of the wall, the soil was the weakest. So it required soil improvement, where the geotechnical engineer for the project decided to use cement stabilized road base, DGB, for a width of double the height or the depth where that soft soil was. So firstly, we removed the soft soil down to the bottom rock, and then we built from there this base of DGB stabilized footing. Same thing was done to the back where the reinforced soil was, where the geogrids were going. But on that area, we've used compacted sandstone, as you see here. To give you an idea of the cross-section of the wall, this is a section at 4 meters in height. That's the wall at the front. This is the footing for the pile for the noise wall, a 5 meter high noise wall at 1.8 meters from the face. And this is the 1 meter fence where it's right behind the block facing. And then there's the service, the grid-free zone for services, the top 1 meter. So knowing the loads, knowing the challenges that the sound wall in particular, noise wall presents, we needed to have a specific design for this wall. In addition, obviously, to the grids that are every 3 blocks, that's the design of the wall. And then we needed to do also extra allowance for the piles under the noise wall. These piles were 2.5 meter in depth, 600 mil diameter. So we looked at stiffening the base and near the top of the piles, and then also looked at extending the no fines concrete, which was only for 1 meter up to here. Well, we extended it right to the 1.8 distance, as you see here, to allow for that no fines concrete also to support, to fill in that gap between the pile and the wall facing. We had these spliced grids at the bottom and the top of the piles, as you see here, marked in red. And we also had other grids in the front of the piles, as you see here, marked in blue. The fence was also allowed for by having sleeves every 2.4 meters, filled in with concrete once the posts of the fence go in. And you can see that the top 1 meter was left with no geogrid reinforcement for future services. The length of the geogrids in this wall were determined by the global stability analysis, where that 70% of wall height we mentioned before was enough to cover the external and internal stability of the wall. It wasn't enough to cover the global stability. So we needed to extend the grids to a 11 meter length at the 14 meter high wall maximum. Some photos to show the actual construction when we were building wall 2. A close-up look here for the grid block connection through the connectors that you see here. It was interesting that before we built the wall, we had some allowances for extra time and effort to build this wall, being the first one we built. However, during construction, we realized that it was going steady and there were no surprises, no delays actually building this wall. The way this wall is built is, as you see here, The geogrids, that's the tensile geogrids, come in with these plastic ribs. So that connector, the blue connector, is to hold on to the rib of the grid. That's how it locks it in place in this recess that is made here for the TW3 blocks. And when it does that, it actually sits flush with the surface of the block. So when the next block comes in, there's no issue in the balance, in the level, and you won't end up with any rocking effect in the block. It's level, and it's just keep on building the next row and so on. The spliced grids that we showed in the previous slides, where the piles of the sound wall were coming, we needed also to build these or install them during construction. So this is for the lower part of the spliced grids around the pile. So we marked the location, we marked the levels, and then we had these grids installed, then backfilled and compacted the structural fill on top, and kept building the wall up to the level where the next spliced grids go, and so on. Then at the end, we drilled through the reinforcement, through the structural fill, down to the required level, which is the 2.5 meter from the surface, to allow for these pile tubes to be inserted and then concreted, as you will see. But this was the way we actually went on building this wall, with step by step, and there were some challenges, some difficulties, but we managed to go through them all successfully. This shows you the where the holes were drilled for the liners, for the pile liners, down to the required level and through the reinforcement and backfill, compacted backfill. And then we used no-fines concrete around these liners to hold them in place and fix them until the time when the wall is finished and the sound wall is being installed. This is another photo showing a line of these pile liners, which were 4.2 meters center to center, 4.2 meters. And this is the wall under construction still, that we will be built up to this level in this section of the wall. These are other photos that are showing the actual spliced grids, how they were placed, locked in by the blocks on top, and then backfilled, compacted of the sandstone. This is the no-fines concrete, where you can see the standard width was 1 meter from the face of block to the back of no-fines concrete, while around the piles of sound wall, we extended that by another 800 mil to give that 1.8 meter supported backfill in front of these piles to the face of the wall. This is a sleeve where we used also for the fence right behind the Keystone wall facing. This is the wall when it was about to be finished. Actually, it is finished here with the caps all put in place. The no-fines concrete, geotextile wrapping, the no-fines concrete to stop any fines from getting into the drainage material, the no fines concrete from the sandstone fill behind it. And you can see the level of these piles all in place. And then this is pretty much a wall, a photo showing a longer section of the wall where we got to the finished level at RW2. I'm going to show you a video of the wall while it was just about finished, showing where showing the scope of the wall, as well as the other walls around wall 2 that we built, just to give you an idea of the scope and location. So in here is where the highest part of the wall is. That's the 336 linear meters. This is another wall, that's wall 3 of the same project that we built as well. And then the next wall was wall 9, which what you see here. Both walls, about 4,000 square meters, were built in about 6 weeks. It was quite a challenge. The client wanted us to finish on time, so we delivered on that promise, and walls were built right on time. But you can see here the sound wall posts are getting installed, and you can see also the scope of the work in here. This wall, that's wall 9, was around the 10 meters high, not as high as wall 2, 14 meters. But it's a great project for us. Photos were taken for the wall after it was finished. So this is where it starts from chain 0, and this is where it gets to 14. This is a 50-meter distance. Just gives you also an idea of how high the wall is. This is the sound wall being installed, right about 1.8 meters behind the face of the wall. This is the fence, as you can see here, right on top behind the wall. And this is 1.8 meters. You can see the 5-meter high sound wall also being built. This is the photo for the highest section of the wall, 14 meters high. Already had visitors to the wall. On the last visit we had to site, and the wall is performing exceptionally well. It was finished September last year, and we do go and see the wall, check on other walls, see wall 2 while we're there at the same time. Thank you very much for listening. We now return to Amanda to introduce the next speaker. Thanks a lot.
Thank you for your insights, Namir. I'd now like to welcome our second and final speaker for today, Gordon Stevens. Gordon is Technical Manager for Geofabrics New Zealand and qualified with a 4-year Higher National Diploma in Civil Engineering, and has been involved in the design and use of geosynthetics into infrastructure projects throughout New Zealand and the Pacific, including Papua New Guinea over the past 30 years. Gordon has presented and arranged numerous training courses on reinforced soil and retaining wall design, and has authored technical papers on the subject. Gordon is a member of the International Geosynthetic Society. Please welcome Gordon Stevens.
Hi, my name is Gordon Stevens. I'm the Technical Manager for Geofabrics New Zealand Limited, and welcome to today's presentation on the Keystone TW3 retaining wall system for engineered structures. We'll start off this session by looking at the evolution of reinforced soil walls, then move on to the design requirements, the components that make up reinforced soil walls, and then focus on modular block walls, looking how facing stability is addressed. We will compare two different connection systems and then finish by looking at a number of international projects where modular blocks with a positive connection system have been used successfully. Now, the commercial use of reinforced soil using industrialized materials started in the early 1970s with metallic strips connected to concrete segmental panels. This is a well-developed system which has good long-term performance on a whole. Economically, reinforced soil has been shown to be more cost-effective than most gravity wall systems once you extend beyond 5 meters in height. Geosynthetic reinforcement followed soon after with geotextile wrapped and polyester strapped walls. The first geogrid wall was built in 1980 using tensile HDPE geogrid. Modular blocks were initially developed as gravity walls by concrete manufacturers for the residential market. The focus of this presentation is in the infrastructure sector, having a higher engineering demand in terms of performance and durability. From a durability perspective, low height residential walls with design lives of up to 60 years typically have a 20 MPa compressive strength requirement. Whereas when you move into highway structures and tall walls, a minimum of 30 MPa compressive strength is a normal requirement. Unlike mortared walls, dry stacked modular blocks are reliant on their plainness and levelness of bearing surfaces, top and bottom. The image shown to the right is of the US Postal Service wall in Atlanta, which is up to 12 meters in height, built in 1990. Within 2 years of construction, cracks formed up to 6 millimeters in width. Now there are many modular block wall systems in the market. The majority of these use frictional connections. These connections are prone to pull out of the reinforcement at the face where low confining stress exists. This is not an issue, obviously, for metallic strip reinforcement, which is physically connected to the facing, but can be an issue for modular block walls. By applying metallic reinforced wall design principles, we have overstressed the importance of rear pullout due to the small surface area and high strength of steel strips, and have not paid much attention to the connection at the face. If we look at the components that make up reinforced soil wall systems, we find they consist of a facing, which provides shape and aesthetics, as well as obviously providing erosion protection to the reinforced soil block. The reinforcement and structural fill that provides stability and controls the deformation. And then the connections, which transfers tensile stresses between the reinforcement and wall facing. For clarity, what is not shown is the drainage system, which is a very important component of any wall system. This would be a whole topic on its own. Now, all standards and guidelines apply the same design approach, which considers both external and internal stability failure modes as shown on the screen. Facing connection is a key consideration for internal stability. If we consider the geogrid to modular block wall connection in design, we have numerous potential failure wedges. If we just consider one of the many potential failure wedges and the consequences of low connection strength, we could end up with failure. Here we have a picture of an example of a real connection failure. The importance of facing connection is further supported by FEM analysis from a paper presented at the 8th International Conference on Geosynthetics, showing high stress areas close to the wall face, those red areas close to the wall face in the green. So facing stability is an important consideration in reinforced soil wall design. The Keystone TW3 wall system is a relatively new system to the market, which incorporates a polymeric connection. This ensures we achieve a consistent alignment of the geogrid with the modular block. Also, an even transfer of load along the full length of the wall, so you don't get a zipping effect. And the connection strength is the same throughout the full height of the wall. With frictional connections, achieving a consistent alignment and assuring a full width of geogrid is available at the connection is more challenging, requiring more site supervision. So as you can see from the image, it is a lot more difficult if you don't have some form of connection in the face for the geogrid to align with. So a wall system with a positive connection is important for tall walls, for high loads such as bridge abutments, and for seismic actions. Here are some examples of tall walls. And here we have some high walls subject to high loads. These include bridge abutments, walls with an uphill slope, and tiered walls. And then we have seismic, which is also an important consideration, not so much in Australia, but certainly in New Zealand, Papua New Guinea, and the Pacific Islands. What we're highlighting in these images is an example where vertical ground acceleration effects resulted in the opening of the blocks, leading to a loss in frictional connection of the geogrid. Notice in the small image to the top right-hand corner, the gravel situated between the two blocks, showing how those blocks opened up. So let's move on to the all-important testing for connection, which is required for each block and reinforcement combination. The results of these tests are unique to the block and geogrid grade. Be careful with geogrid manufacturers who operate different factories international. A lot of testing of these systems is normally carried out in the United States, so it's based on product manufactured and supplied in the USA. It's not possible, for example, to use the test data for mirror grid polyester geogrid manufactured by Tenkata in the US with a mirror grid manufactured in the Asian factory. The products are clearly different and require individual testing. Furthermore, each product and grade have to be tested to obtain the connection data for design. So here we have a cross-section and plan view of the test apparatus. The blocks are positioned. The geogrid is sandwiched between those block layers, and a normal load is applied to match the varying wall heights for the wall system. A pull-out force is then applied at a constant rate of 10% per minute, and this measures the ultimate connection strength and the serviceability connection strength, which is typically at around about 19 millimeters of deformation. The results are then plotted with normal load on the x-axis and connection load on the y-axis. Here we have a frictional connection plot showing the dependency of the normal load to achieve that connection load. Whereas the positive connection, we have a constant throughout the full wall height. So at all normal load levels, the connection load is a constant. So how does this apply when you design these walls? What is shown are load envelopes for both the frictional and positive wall systems. So starting off at the top, the frictional connection, what we find if we have a failure wedge is that failure wedge cuts through the geogrid as circled there and ends up going straight up and finding its way to being governed by the pull-out at the facing. So that point at that slope on the facing, so the strength at that point where the failure wedge cuts through the geogrid is governed by facing connection. If we look at the same failure wedge cutting through a positive connection geogrid and take the line up, what we find is that the strength of the geogrid is governed by its long-term design strength. So what we end up having with a positive connection is that we have more efficient use of the geogrid strength. Of course, the wall batter has an important influence in this connection strength as it impacts the normal load being applied. The steeper the wall batter, the less number of blocks are applying a load on the geogrid. This is normally referred to as hinge height and is an important consideration, especially where you have increasing wall batter, 6 degrees or higher. It can have quite an influence in that normal load for connection. Obviously, seismic performance is also a consideration. So in the next few slides, we'll have a look at some seismic testing carried out on a full-scale reinforced saw wall in Russia. The wall height was 3.5 meters with a sand backfill, and TW1 facing block was used with a polymer connection. This was reinforced with 8 layers of tensile RE520 every third block, with a reinforcement length of 3 meters, which is roughly a length to height ratio of about 0.86. The total weight of the sand and facing was around about 100 tons. Here we show some plots of the vertical acceleration on the left and the horizontal acceleration plots on the right. And this structure was extensively monitored for deformation and soil pressures. And a number of earthquake examples were run through. So these plots are just for one earthquake series, earthquake 5. Here we actually show the results for the earthquake 6, which was the highest accelerations. So 0.63 for horizontal and 0.7 for vertical. So the permanent deformations after the test were less than 2 millimeters between the top of the fill and the facing blocks. So that's after that 0.63 horizontal and 0.7 vertical. So you see the plot on the right of the wall, and the dark line represents the residual movement of the facing. So you can see at the top it's just less than 2 millimeters, and the light orange line shows the actual movement or deflections taking place during the excitations. So in summary, the tensile block wall system performed very well within its serviceability limit conditions following the 6 simulated earthquakes. And this is very much in accordance with what's been observed in the behavior of these structures that have survived earthquake events. And essentially, we can conclude that the whole system, the geogrids, the blocks, the soil, works as a composite and moves as a composite under these seismic events. So now that we understand the importance of testing for face connections, we need to apply this into design. For the purposes of this presentation, I've looked at an 8-meter high wall, considering a traffic load, a level crest, and a firm foundation. Based this design on a 100-year design life in a gravel fill. I've followed the AASHTO limit state design approach, LRFD method, so limit state similar to AS4678, and I've used the MSc software from Adama Engineering, and I've considered both the Keystone TW3 positive connection wall system and a typical frictional wall system. So here we have the results for the positive connection. We have the geogrids at a constant 3-block spacing. We've only used 2 grades of geogrid to achieve quite an efficient design. So you can see that the capacity demand ratio, which is similar to the R star, S star, and AS467. So if you look at that for connection strength, the numbers are very similar to the geogrid strength requirements for design in those columns. So that suggests a good efficient design, and we have a total reinforcement strength for the wall of 457.9 kilonewtons. If we now look at the frictional connection, what we see is a requirement to change the spacing. So we now have to go to 0.4 meter spacings in the lower part of the wall. We still have 2 grades, but those grades have to be of a higher strength, and we've had to increase from 13 layers to 15 layers. And as you can see now, the CDR strength for connection is still very similar to what we got previously. However, the CDR strengths for the internal strengths are much higher. So we've got a lot of excess capacity in the internal strengths. So a less efficient design. The design is very much governed by connection. And you can see that the total reinforcement strength has increased from 457 up to 956 kilonewtons per meter. So essentially, we're paying for a lot of extra strength that's not being fully utilized in the design. So let's look at a few completed structures. And we'll start off with a project here in New Zealand. It's a council project down in Dunedin on a tourist route out to the coast to the albatross colony. The location of this key route is over some variable tuff rock, and this required various or numerous inspections to verify the acceptance of the foundation for this wall. The structure required a vertical facing and the use of a high quality granular fill because the wall actually extended in construction into the winter months and it needed to be kept open. The road needed to be kept open for the full construction. So there was quite strict constraints around the construction of this wall and keeping the road open. Moving on to the next structure. This is a structure in South Wales in the United Kingdom. The structure had a number of challenges. First of all, the site was constrained by the carriageway and that bold red line to the left of the site, and by the river Usk to the right of the site. There was level differences of up to 9 meters and high level of differential ground conditions. Keystone TW3 solution was selected for this site as it saved up to 8 weeks of piling time. What we can see from the boreholes over the site is the variable nature of the ground, with the bedrock dipping away to the east. The design considered a load of around about 350 kPa at the base of the bank seats. As a result, you can see a high density of reinforcement below this high load. And the granular fill consisted of a imported high quality fill having a friction angle of 38 degrees and a density of 20 kilonewtons. So this was used in the bridge abutment zone to control the differential settlements, a lightweight fill having a density of between 300 to 500 kilograms per cubic meter was used. This was a lightweight expanded clay aggregate that gets used fairly substantially in the United Kingdom. Here are some images of the bridge abutment to the left and the approach walls to the right. And this solution essentially solved a lot of the total and differential settlements for this particular site. Now moving from South Wales to New South Wales, and this project has already been covered by Namir, but what I'd like to highlight using the tensile soil software, and you can see the screenshot from the tensile soil software, and following the AS4678 guidelines, is the impact of a low confining stress in the wall stability. So what we see are the results for the Keystone wall with a positive connection, showing acceptable results with all factors for external and internal being achieved. However, if we change the design to a frictional connection, what we see is a number of failure wedges highlighted in red in that top zone as a result of that uphill slope. So highlighting the importance of that positive connection. Moving from New South Wales back to South Wales, we have a regeneration project to replace and extend derelict walls to create land for new business development. The challenge for this hydraulic project was restrictions from the Environmental Agency around working in the stream during the winter months. Using a Keystone TW3 wall system removed the need for piling, and no heavy plant or temporary works were needed, resulting in low pollution risk to the river. Good quality fill and the ability of the wall system to match the curved profile of the river were key criteria for a successful outcome. Now what we have is a load-bearing bridge abutment. This is on the A24 in West Sussex in the United Kingdom. So we had high bank seat loads to be considered for these abutment walls. The design followed BS 8006, and there you can see the drawing from the completed structure. The key requirement for this part of the new junction was a busy dual carriageway, which had to be built quite quickly with minimum impact on both the main development works and traffic flow along the trunk road. The Keystone TW3 solution reduced the number of crane lifts and kept the A24 lane closure to a minimum. Once again, a high quality Department of Transport type 6IJ aggregate, less than 75 millimeter in particle size, was used for the fill for this abutment. Here we have the walls later in construction, so you can see the prep for the bank seats and placement of the bridge deck, and the completed structure on the right with the bridge deck. And here is the final completed structure, fully operational. Okay, so moving on to the last structure, what we'll look at, and this is the highest of all the structures that we're looking at. Before I get into it, I'd like to acknowledge Yuli Duala Rigby, who's the Chief Engineer at Tensar, for providing the background for this impressive project and all the wonderful photographs. So the Fujairah Freeway in the UAE connects Dubai in the west to Al Fujairah on the east coast. This project involved an extensive cut and fill exercise through the very mountainous area to the west of Fujairah in order to form a new 4-lane freeway. Either way, 10 lanes in total. Constructing bridges to pass these highly eroded valleys would have been an incredibly costly exercise and result in the contractor. As a result, the contractor looked to utilize the local cut through these high mountainous area to form massive earth retaining structures. So utilizing the Site 1 Gabbro substantially cut carbon emissions by reducing the transport costs to and from site. So everything was blasted and crushed on site. A total of 26 walls were constructed with a combined area in excess of 80,000 face square meters. A mixture of walls were constructed, with the largest being a 3-tier wall forming an integral structure with a cumulative height of up to 60 meters. As with any design, it's important to look at the full picture. So looking at the internal structures in terms of internal wall stabilities, and then looking at the structures in a more holistic, combined manner. Very important from a design perspective. For the site, drainage was a critical factor, and the contractor elected to use a lower quality, freer drainer fill in the sort of core of this large embankment. This necessitated the use of a cement soil mix to seal off the wall crests to minimize the penetration of water into that fill. The reinforced fill for the actual walls was a crushed gabbro up to a 37.5 millimeter particle size with a minimum CU of 5. The friction angles for this particular material were in excess of 45 degrees. However, from a design perspective, a friction angle of 42 degrees was used. Quality control was important, especially around placement of the geogrids. We had geogrids up to 35 meters in length, and these had to be pulled taut to remove any wrinkles, ensure they stayed in place for the filling and compaction process. During construction, a rockfall event happened, and these things can happen. These unexpected events can happen especially on large sites, and this resulted in dislodgement of the facing blocks. The image, what we see here, highlights the importance of good compaction and good workmanship. So essentially all we lost were the blocks in the facing. The actual fill behind was very competent. And what we see here is the repair to that section of the fill. One of the issues with this area is that it's very much prone to flash flooding. And this, in this image, what we can see is the same wall type in another site in the UAE. So the lessons learned from this previous project were applied to this more recent project. And here what we see is implementation of scour protection using gabions along the base of the wall to protect the foundation from these unexpected storm or scour events. So what we see here is a view of the near finished walls. An average install rate of around about 50 face square meters was achieved for this particular project. So some lessons learned from all of this. An efficient design is very important because what you end up is with less geogrid and lower strength and a more cost-effective solution. So the geogrid is there's less handling by the contractor of the geogrid. Connectors are very important to get a good, efficient load transfer at the face, and it helps reduce construction tolerance at connection issues. A high quality fill reduces the risk and variations in strength over time that could lead to face deformations. Foundation competency is essential for all walls. Dry stack walls are very much reliant on a competent and level foundation. So key area for any walls, but more so for modular block walls. Internal, compound, global stability are all required in reinforced soil wall design. And it's important to test your designs using different load and water condition scenarios. Redundancy is also an important consideration. As with the large structure, even though shear box tests showed friction angles of up to 56 degrees, the design adopted a 42-degree friction angle. So it's quite handy to have that level of redundancy in your design. And once again, it's important to take a holistic view of subsurface and surface drainage for the whole structure. Can't emphasize more the importance of proper drainage and taking that into account in design. And of course, you need to protect the foundations. The foundation of any wall is a key area, a high risk area, and especially if you have a site or wall that is prone to scour, then you need to protect it, and gabions are a good solution for protecting these walls. So thank you very much for your time, and we'll now go back to Amanda to start the Q&A session.
Thank you to our speakers for some great presentations and insights this evening. I'd also like to thank everybody for sending through so many questions. It's really encouraging these levels of engagement. If you would like to submit a question, there's still time. Just put it in the YouTube chat box. Thank you to everyone who also sent through questions on registration. And we might start with one of those. And one that I particularly was drawn to, which is around quality in construction. We're talking a lot about this at Engineers Australia. And I have got a question that's being directed to Gordon. So stay where you are, Gordon. It's around What is the durability of this type of construction? And do you get 100 years of life? Thank you, Gordon.
Thank you. Thank you, Amanda. Yeah, look, these structures are designed. These are engineered structures designed for highway works, and for any highway works, a 100-year design life is a prerequisite for these types of materials. So the concrete facing the blocks typically have 30 MPa, and the TW3 wall system has been independently reviewed by the British Board of Agrima in the UK and has a certificate for 120-year design life. The same applies to the tensile geogrid, which also has the same BBA certificates for walls and bridge abutments for up to 120 years. So these are engineering structures. So it's certainly an important question, and they certainly satisfy those criteria.
Thank you for that. And
Thank
sort of
you.
staying with our quality theme, we've had a great question that's come in from Hilton, directed to you, Namir. And Hilton is asking us, what are the advantages of Keystone over reinforced concrete, please? How do costs for Keystone stack up compared to reinforced concrete or twin fabricated formwork? Thank you, Namir.
Thanks, Amanda. It's a good question. Definitely, it's the area where we as contractors deal with every day. The advantages we find with Keystone are mainly in the ease of construction and the speed of construction. The materials, in comparison with other systems, are mainly very cost effective. In terms of the materials, the wall components, geogrids, keystone blocks, backfill materials, the construction itself is easy because you don't need any special equipment, machinery. You don't need any cranes. It's really all hand placed. The availability of block is always there. You don't need to wait for leading time, weeks or months even, to make the facing. It's already always available in stock. In case the stock is not there, the blocks can be made within very short time frame. It is the best option for us as the contractors. It is the best option in field situation where Keystone and geogrids work really well in terms of number stacking. However, in cut situations, we also find that many cases Keystone becomes really cost effective. In comparison with concrete walls, you're talking about a foundation that is reinforced concrete. And that's where a lot of cost goes into this type of retaining walls. While with Keystone, you don't need any concrete base. All you do is it's a base leveling pad, can be plain concrete, no reinforcement, or can be compacted fill. So again, it comes to also the application, but we find that Keystone is a very good solution to be offered. Thank you.
Thanks, Namir. And just following on from that, in your presentation, Mario from VDN Consulting Engineers, good evening, Mario. He sent through a question asking you, were other types of retaining wall systems considered here?
Yes, there were. As I said, being the contractors, we always look at what's the best option in terms of first the performance, constructability, and then the cost. We looked at other types of conventional Keystone with the other types of grids. The client wanted to have the Keystone finish on this project in Oakdale, so looking at other options wasn't really in our intention. However, we designed the walls first using the conventional Keystone system. And then we realized, because of the high loading, because of the nature of the wall, the height of the wall, we assessed the TW3 option and found that it is definitely the best option for that wall in particular.
Thanks, Namir. And Gordon, I'd like to bring you back into the discussion. We've had a great question from Russell in WA, and Russell's asking, Gordon, under what circumstances would you recommend a Gabion wall for a wall less than 10 metres high, retaining wall?
Yeah, look, with any reinforced soil structure like a Keystone TW3 wall, you're very much reliant on a well-compacted backfill material. So if you have a remote site where the quality of the material is such that it is problematic for compaction, or the compaction equipment that's available on site is of an insufficient compactive ability to achieve the required density, then a retaining wall like a Gabion mass gravity retaining wall can be the better approach. Also, where you have cut slopes where it's not possible to achieve the reinforcement length required for stability, then mass gravity walls, once again, like Gabions, are perfectly suitable. And certainly, 10 meters high Gabion walls have been built as mass gravity structures 10 meters and higher. So can be done, but it very much comes down to your particular site conditions.
Thank you.
Thanks.
And staying with you, Gordon, we've had a question coming from Sam, and Sam's asking, what are the key factors for to avoid overturning and sliding large-scale retaining walls? Gordon.
Yeah, look, Sam, it's a very important question you've raised, and I suppose I could go on for half an hour, which I won't, answering this question. First of all, when it comes to overturning for reinforced soil structures, it's not normally a standard failure mode. You'll more likely get a bearing or a global failure than an overturning failure. Overturning tends to be associated more with mass gravity cantilever type walls. So you'll always find that you're on the safe side when designing these MSC Keystone TW3 type walls. Sliding is another kettle of fish, however. And sliding can be influenced by the type of fill along the base. So if you've got a fine grained material, that has quite a dramatic influence in the interface friction between the reinforcement at the base of the reinforced soil block and the foundation. And that can result in a longer length of reinforcement. So the typical length to height ratio for these structures is around 0.7, and that's a minimum certainly for areas with seismicity, but that can increase to maybe even a length to height ratio of 1 where you've got poorer ground conditions. And then with seismic, once again, it can have an influence on sliding, and it becomes a key criteria. But then that's once again a whole new design methodology where you're starting to use moving away from pseudostatic methods to displacement methods to determine your required reinforcement length for sliding. So interesting question, and is well addressed in most design methods, BS, AS 4678. Thank you.
Thank you, Gordon. And we are getting some great questions, very interesting questions. We've got a question coming, Namir, around high loads, and the question is around RSE. RSE is subject to high load. How do we define high load? And why use block and not RC panels? For 14-metre high, will flexible strip footing settle result in a wall collapse? Thank you for that question.
Thank you. Quite a good question. And it's with regards to the footing, the Keystone is founded on flexible base leveling pad. Whether it's concrete or it's compacted fill, it is made to have flexibility. Therefore, if there's any differential settlement, if there's any movement in the wall, this base leveling pad is there to absorb that movement. Let it happen. If it's rigid, reinforced concrete, like with other types of retaining walls, you will end up with all sort of problems. Wall tries to settle, doesn't have room to go down, moves to the front, or there will be all sort of deformation. While the flexibility that MSE walls offer absorbs that movement, and it's quite clear in earthquake events where things horizontal acceleration happens, and with that flexibility in the MSE walls, you would get these walls to perform really well. I'm sorry, can you repeat the first question, Amanda? What was the first question?
The first part of the question.
Yep. I think the high loading.
Yes, we were talking about
high loading. Sorry, yes. With regards to high loading, we identify high loads as loads that we need to allow for in our design that are higher than the usual load. So we normally allow for 5-10 kPa live loading in the standard design. However, we get some designs that ask for 20 kPa, which is becoming the norm. Then we get something like 35, 55 kPa, which adds more challenge to the design. What do we do here, And that classifies as the high loads, which results in at the end in longer geogrids. MSE walls can still be designed to higher loads, but we need to do something to allow for these loads. And with that, the extra length of geogrids, more layers of geogrids depending on the design, the soil parameters, the height of the wall. These become definitely are part of the area where we look at in the design stage.
Thank you, Namir. And we have a couple of questions here, and I'll just summarise it with Sharon, who's saying, is this a cost-effective system compared to other types of retaining methods that could be possibly used here? Great question.
Thank you. That's a question for me, Amanda?
Yeah, Namir, thank you.
Okay, thank you. Sorry. Cost effectiveness is definitely the area where we look at, as I said before, as contractors, because we've got to make things attractive to our clients, win the job based on performance, design, as well as the cost. Where Keystone becomes a cost-effective option is in a fill situation. That's where using geogrids, backfill materials, and the Keystone blocks become really the best option, or one of the best options. If it's in a cut situation, it becomes a bit too tight, and where if you don't have enough room behind the wall, even if it's in a fill situation, where you have a building or a road or other structures, that you don't have room for the geogrids, then it becomes it doesn't offer that cost effectiveness. But we find, like in our business as UCBC, we find that Keystone forms about 70% of our business. And there's always a solution with the offering Keystone. It is that flexible that you can do geogrids, no fines concrete. In the geogrids, there's the TW3 now that we're getting more familiar with and getting more used to pricing, designing, and building. It is very cost effective. Thank you.
Thank you, Namir. We've had a question that's come in talking about water and erosion, and thank you, Kai, who's based in WA. Gordon, how to control water and erosion?
Thanks for that question. As everyone is probably aware, when it comes to failures of any retaining or reinforced soil walls, water tends to be the predominant failure mechanism or source of the problem. And certainly, if you're in any hydraulic situation where you have water and the potential for erosion, then you do need to address that. It's critical. The structure on its own can't provide that protection. And as shown in the last case study in my presentation, the use of some form of rock mattress or gabions to protect the foundation, to prevent scour and undermining of the MSE wall is paramount, and that needs to be evaluated. The potential for scour, so the erosive nature of that soil at the toe, and what level of protection is required, how far it has to extend outwards to protect the foundation of the MSE wall, and then obviously at the top of the structure as well. Especially if there's uphill slopes, controlling water down those uphill slopes by having interceptor drains, swell drains, is once again very, very important. But certainly the most critical area is in that foundation area, and protecting that toe from erosion. But really, it's one of the most important areas, the foundation for any wall structure, and a very good question. Thanks.
Thank you. And just staying with you, Gordon, a great question coming in from Simon. And Simon's asking, Gordon, under what circumstances is plastic the preferred reinforced material? Thank you, Simon.
Yeah, Simon, just a small correction. I prefer to call it a polymer because it sounds more engineering than plastics. Plastics don't always have a great name these days, but these are engineered polymers, and they perform in a wide range of soils. However, when it comes to steel reinforcement, steel has a problem when you have soils that contain salts. So once again, in the Middle East, where you've got Sabah sands, they're high salt content, and that's where these polymer materials are very much preferred. If you've got a gravel source where the geology is a more acid-bearing rock, having a sort of pH of less than 6, then steel can't be used. You need to use polymer reinforcement once again. And where you've got high plasticity index, higher than 6, or soils with low resistivities, then plastic or polymer materials are preferable. So it comes very much down to the actual application and the source materials, because you've got to remember that with these structures, the fill material is represents over 90% of the volume, and it has a high impact in the cost. And so there's a big commercial advantage using these polymer reinforcing materials over other materials around the use of a wider range of fill types. You require very specialist, high engineered fill types for steel reinforcement for obvious reasons. So yeah, interesting question that, and thanks for asking that, Simon.
Thank you, Gordon. Moving on to safety and performance, we've had a question come in from Karthik. Good evening, Karthik in WA, asking, Namir, how important is safety and performance of geosynthetic walls for industry? Thank you.
Thanks very much. Very important. In terms of safety, you want to have the materials that you use in your structures safe to work with, safe to perform throughout the design life. And and I'm not sure if you also cover safety as the safety of the construction of these retaining walls, but safety is definitely the comes first when it comes to the construction of these walls. If we're talking about the performance and the longevity of these geogrids, they are the structural part of the wall, so their performance is definitely a big part of how the overall structure works. Hope that answers your question. Thank you very much.
Thank you, Namir. We have had a question that's come in, and we've had a few questions like this. I'm trying to wrap them up, and maybe, Namir, you can continue the conversation. And the question is, what are the main benefits of the Keystone system? When should Keystone system be implemented? And that's come in from Seeming in Victoria. Thank you.
Thank you very much. The main benefits we find with Keystone are in the aesthetics, the cost effectiveness, the flexibility in the design, and the adaptability to what's available in the market. You can get different shapes, finishes, and the aesthetics. The constructibility is always for us as UCBC and for many other players in the market as a high production type retaining wall. Then it's always, as I said before, always available in the market. You don't have to wait for any manufacturing leading time. It's always in the stock with the manufacturers, and the actual ease of construction is another point, that you're using the same block from the first row to the top, the exact same block. You're not changing different blocks, different items, and you just get used to doing the fast construction because you don't have to wait for anything, or there's no surprises, in other words. The other thing is the way that you can design Keystone walls, especially now with the TW3 system, gives you a wide range of options. So you can build a wall that's 2 block high, and you can build a wall that's 14 meters high, as we did in Oakdale. So it's that, again, that range that Keystone walls can cover. Plus, it's been tested for about 30 years now, 40 years around the world, and the performance of these walls are there. You can manage, you can monitor, you can check. So there's no hidden facts in there. It's been around for a long time, and it only gets better every day. So I hope that covers the answers for your question. Thank you.
Thank you, Namir, for that comprehensive answer. And we have had so many questions, and we have run out of time. So I think we will need to do some more webinars on this topic, and hopefully our speakers will come back and help us do that. So please, our audience, join me once again in thanking Namir Asmaro and Gordon Stevens for their time and sharing insights at today's session. I'd also like to thank Engineers Australia, long-standing industry partner Austral Masonry, for making tonight's webinar possible. For more webinars in the Engineer Speaker Series, please follow the YouTube link in the description box. We've also, please don't forget to register for the upcoming Non-Combustible Facades webinar, which is scheduled for the 15th of April, and we look forward to seeing you there. As always, at Engineers Australia, we're on a continuous improvement journey, and we'd love to hear from you. What do you enjoy? What can we do better? So if you could please complete the short feedback form, which is linked to the description box below. To close, I'd like to thank everyone for joining us here tonight. I hope you have a lovely Easter, and I look forward to seeing you at our next webinar. Thank you and good evening.